shall be showing you how to drive a formula for an induced EMF in an electromagnetic induction. I've seen a particular question which shows that we are to show that the induced EMF of an electromagnetic induction is alternating. You know how an alternating or a sinusoidal motion, form of a particular wave is. So I am going to show, considering this diagram on the board, you see where this end is number of turns around the conductor. You can see the conductor up there. B here represents magnetic flux density, and this one here is the cross-sectional area of the conductor. This one, this angle theta here, represents the angle in which the conductor is being placed. And from this, if you are to find the magnetic flux of this particular, you know there is a combination of electric field and magnetic field here. If you are to find the magnetic flux of this particular system here, you will have that your phi is equals to NAB cos theta. Let's label this as equation 8. And you know that in a length law, where length shows the direction of motion of an EMF to the force density, magnetic force density in a particular electromagnetic field, it says that the E there is equals to minus d phi all over dt. And in this, if we are to put equation A in B, we will have that our E will be equals to minus d, all of this now, replace the phi. You have NAB cos theta all dt. You have it as this. That is to show that we are differentiating this particular function with respect to t. And you know that in waves, if you have an angular velocity as this, is equals to theta all over t. And if I manipulate, I will have that my theta is the same thing as omega t. So that when I put it back into this equation, I will have my E, which is the induced EMF, is equals to minus d into NAB cos omega t. Now all divided by dt. You can see confidently you can differentiate this function, which is equation C, with respect to what? T. How will we do that? That is what I'm going to show you now. You can see that your A, which is the number of turns, it doesn't change. The cross-sectional area of the conductor doesn't change. And the magnetic flux density, so long as the system is concerned, it doesn't change as well. So you see that these three are constant. There is nothing wrong with bringing them outside, because if you differentiate them, they are going to be 0. So you have this one to be outside, so that you have your E equals to minus NAB, then you have your d cos omega t, and all over what? dt as this. And looking at this, you can confidently differentiate this with respect to t, no problem. Yes. So that what is the differential value of the cos omega t with respect to t? You know that this omega here is a constant. You bring it out here so that you will have your induced EMF is equals to minus NAB omega times the differential value of a cos is minus what? A sine. So you have minus sine omega t. Now look at this. This is not as if it has a particular mathematical proof, but it is a constant. If you go to the differential or derivative constant, you will see whenever you are differentiating a cos, it will give you a minus sign. When you differentiate a sign, it will give you a cos. So if you are differentiating this now, it will give us a what? A minus sine omega t. With this constant here coming back here. So you have this as this. Since your n, a, b, and omega, all of them are constant, you can let it to be the peak of the oscillation, which is what? You can say let E naught to be equals to what? N, A, B, omega. So that if you put it back in the equation, you will have your E now to be equals to minus E naught multiplied by what? A minus sine omega t. Negative multiply negative, you have a positive value. So you have this one to be equals to your EMF now. Induced EMF will be equals to this multiply this, you have E naught sine omega t. You can look at it, this equation now is a sinusoidal equation, which shows that this is an induced EMF, this one is the peak of the oscillation, and this one gives you the angle in which the oscillation takes place. And look at it, it has no phase angle. No phase angle is the same that is in phase. So if you are to draw this particular this now, you can see it will take a sinusoidal oscillation as in this form. You have this, and this is your E, this is your point of starting, and this one like this goes up and going down, and you have this as the peak. That is the what? The maximum displacement of the wave. Thank you for watching this video. You are welcome to my channel. Always subscribe and click on the like button.